Hello everybody and welcome back. Page 319, Acid-Base Chemistry. Module 10. We're going to go all the way to example 10.3 today. So we're going to cover more or less half the chapter. What are we covering in this module? Well, acid and bases, definitions and so on. Behavior of ionic compounds in aqueous solutions, so in solutions in water. Identifying acids and bases in chemical reactions. Predicting the reactions that occur between acids and bases. Reactions between acids and bases. Molarity, the dilution equation. The importance of concentration. Using concentration in stoichiometry. And acid-base titrations. So if you don't remember stoichiometry, go back and review this module 6, I think. Go back and make sure that you understand stoichiometry because we're going to be using it again. So let's look at physical characteristics of acids. So general characteristics of acids, you're going to find that on page 319. You need to know these. Acids taste sour. You're not going to put them in your mouth unless it's a food acid, and then I'll tell you it's okay to put in your mouth, like in a lab, for example. But in general, you don't put anything in your mouth to taste because some things in chemistry can be poisonous to you. Number 2, acids are covalent compounds. And remember that covalent means that you have two nonmetals bonding together using covalent bonds, meaning they are sharing electrons, but in a way that they conduct electricity when added to water. We'll see how this works. Number 3, acids turn blue limeous paper red. So here you have limeous paper. It was blue, and when it touched the acid in the beaker, it turned pink. It's red, but pink is a shade of red. Okay, we'll see what limeous paper is. Now, limeous paper is a type of indicator. So page 320, you have a definition for what an indicator is, and you need to know the definition of an indicator. An indicator is any substance that turns one color in the presence of an acid, and then it turns a different color in the presence of a base. And here you have examples of indicators. Methyl orange, bromophenol blue, thymol blue, phenolphthalein, alizarin yellow. And litmus paper is another indicator, one which you're going to be using quite a bit in this module. So here you have the pH ranges and the color they turn when they get into contact with an acid, and then how they change to a different color when they touch a base. So methyl orange, for example, is orange in the presence of an acid, but it turns yellow in the presence of a base. Thymol blue, it's yellow in the presence of an acid, but blue in the presence of a base. Do you need to know the colors they turn? No. Do you need to know all the names of different indicators? No, those are just examples. But you do need to know the definition of what an indicator is. It indicates the presence of an acid or a base by changing colors. Okay. You also need to know the general or physical characteristics of bases. What is a base then? Bases taste bitter. Once again, you're not going to put anything in your mouth to see if it's a base. Number 2, bases are slippery to the touch when dissolved in water. And 3, bases turn red litmus paper blue. Pink paper called red paper. And it turns blue when it's touching a base. And you need to know the definitions, the general definition of a base. Okay. You are going to perform experiment 10.1 this week on page 320. The title is Common Household Examples of Acids and Bases. So you're going to take several substances: orange juice, toilet bowl cleaner, bar soap, all-purpose cleaner, drain, unclogger, and then you're going to test to see if these are acids or bases. Remember not to put anything in your mouth. Remember to wear goggles, and remember to put gloves on when you do this experiment. We'll talk about the results, the observations, when we meet for our Zoom meeting before you turn it in for grading. And if you have questions this week after you have done the experiment, email me. Okay. Not only do you need to know the general definition for an acid and a base, but you also need to know the chemical definition of an acid and a base. And you're going to find those on page 322 plus, more than one page explain these, in your textbook. So let's see. Acid. What's an acid, chemically speaking? Well, an acid is a molecule that donates hydrogen ions. It's called a proton donor. A hydrogen ion, another name for a hydrogen ion, is a proton. So they donate, they give away hydrogen ions. They give away protons. A base, on the other hand, is a molecule that accepts those hydrogen ions. It's called a proton acceptor. One gives them away, one takes them. Match made in heaven. So they do react together, and you'll see how the reaction works soon enough. Okay? So here we have hydrochloric acid reacts with water. The hydrochloric acid is the acid. So it gives a hydrogen ion to the water, the water becomes a hydronium ion. So it has now an extra hydrogen ion, which is positive, and the whole molecule becomes positively charged by 1. What's left when you break the hydrochloric acid? Well, the chlorine right here, the chloride ion, which is a negative ion. So that's going to be left in the solution as well. Here you have a representation, Lewis representation of the reaction. Hydrochloric acid, the water, will yield the chloride ion, negatively charged, because it lost a hydrogen, and the hydrogen went ahead and bonded with the water, creating that hydronium ion. Okay? So this is an acid-base reaction, and you'll see them in more detail soon enough. This is just an example. The water here was acting as a base. It not always acts as a base. Sometimes it acts as an acid, and that has a name that you're going to have to learn too. But in this case, it was a base because it was accepting those hydrogen ions. Another example, here you have your water, you have your ammonia, and what happens here? Look at this. The ammonia is your base, and here your water is your acid. The hydrogen, one of the hydrogens from the water, is going to leave that water and attach itself to the ammonia, to the base. Here you have it. When the base, the ammonia, loses one of the hydrogens, it becomes an ammonium ion. It's a polyatomic ion that's in your table. And the water, when it loses that hydrogen, it becomes a hydroxide ion, which is also in your polyatomic ion table. Okay? So here's the Lewis representation of the reaction, and here's the reaction itself. The water was the acid here, donating one of the hydrogens to the base, which was the ammonia, to give you the ammonium and the hydroxide ions. Whomever gives the hydrogen is the acid. Whomever receives the hydrogen ion is the base. Just follow that hydrogen to see who is giving it, who is receiving it, and then you know who the acid is and who the base is. Now, compounds like water that sometimes act as a base and sometimes they act as an acid have a name. They're called amphiprotic compounds. You need to know the definition that's on page 324 in your textbook. An amphiprotic compound, also called amphoteric compounds, okay? So both of them are the same, mean the same, is a compound that can act as either an acid or a base, depending on the situation. So basically who they are paired with. If the water is better at attracting those hydrogen ions, it'll act as a base. If it's better at, the other one is better at taking those hydrogen ions, it will act as an acid. It just depends on who it's paired with. Now, page 324, behavior of ionic compounds in an aqueous solution, so a solution of water. And you have, look at the picture. You don't have a picture like this exactly, but follow along. When ionic compounds, remember that an ionic compound is a compound made out of a metal and a non-metal, and what keeps the two together is the electromagnetic, well, the electrostatic forces. One is positive, one is negative, and they are attracted to another, and that keeps them together. Here you have it. Positive, negative, they are attracted to each other. It keeps the molecule together. This is supposed to be sodium chloride, which is your table salt. It's a crystal structure, so they make these kind of cubes, okay? These kind of cubes, very well arranged, is a crystal. So when ionic compounds dissolve, meaning they get into the water and then they're being pulled apart and they seem to disappear in the water, okay? They split into their constituent ions. So basically, you see the sodium is represented by the positive, because if you split this, the sodium is your metal, and that means it will be positively charged, and your chlorine, the chloride ion, is represented by the negative sign right here. So now you have water. Here's your water, which is a covalent compound represented by a red ball, which is the oxygen, and the two white balls that represent the hydrogen, okay? And remember that this is dipolar. They're sharing electrons, but not equally. The oxygen holds onto them for a longer period of time, and the molecule develops a partial charge here that is negative, while the hydrogens on this side are partially positive. Okay, so the water molecules come in between these ions and break them apart and then surround them. See, they're being surrounded by molecules of water. Look the way they are being surrounded. If you're a positive ion, so in this case a sodium, the molecule of water, that's the side of the molecule of water that's facing it, is the negative side, so the oxygen side, because opposite charges attract one another. If you are the chloride ion, which means that you are negatively charged, look who is facing, what part of the water molecule is facing that chloride. Those are the hydrogens. That's the positive side of the molecule, because opposite charges attract one another. So let me read this again. When ionic compounds dissolve, they split into their constituent ions, and these electrical charges are now free to move. In other words, they can conduct electricity. If you remember, that was one of the physical characteristics of acids as well. Okay? So if you're an ionic compound, you can conduct electricity. In a minute, we're going to see how acids conduct electricity. Now, you will need to be able, for this section of the module, to identify acids and bases in chemical reactions. page 325. Follow along, okay? So number one, identify who is giving that proton ion, that hydrogen ion. Remember that another name for a hydrogen ion is a proton. So who is giving it away? That will be your acid. Now identify in that reaction who is accepting that proton ion. That will be your base. Remember, acids are called proton donors. Bases, another name for a base, is a proton acceptor. And here it says, be very, very careful of spectator ions. And what are those? Well, those are ions that do not participate in the reaction. Here you go. You need to know what a spectator ion is. You need to know the definition, and you need to be able to spot them in a reaction. So what is a spectator ion? In ionic precipitation, so basically you have an ionic compound in an aqueous solution, there are often ions that are not involved in the reaction, and these are known as spectator ions. Look at this reaction right here, okay? So the spectator ions are easily identified using the ionic equation. You have to break everything into ions. So here's your sodium and your iodine, your silver and your ammonia, polyatomic ion, and so on. So you break everything into the constituting ions, all the ions involved in there. And then you need to spot those ions that appear in the reactant side and also appear in the product side. Sodium is here, is also here. The nitrate ion is here and is also here, okay? So those are your spectator ions. This equation shows that the silver, here's your silver, and the iodine, right here, have reacted. Okay, here you go. It's one of the products. Joining together to make that precipitate. So basically they go at the bottom of your aqueous solution. Remember that AQ in parentheses means in aqua, in water. So this is solid and this is in aqua, in water. So this solid has precipitated to the bottom of the beaker. Well, the sodium and the nitrate ion, are spectator ions. They did not participate in the reaction. They were there at the beginning and they are dissolved in water at the end. So basically you can simplify this reaction as the iodine ion got together with the silver ion to make this silver iodine. Okay? Solid precipitate. So spectator ions, find those ions once you break the equation into the components, into the ionic components, will appear both in the reactant side and in the product side, and they can be ignored. Okay, you can ignore them. Now let's apply what we have learned to an example, and then we're going to do some extra practice problems you can do on your own later at home. Example 10.1 is on page 325 in your textbook. It says, determine which reactant is the acid and which is the base in the following chemical reactions. And we have 3 to work through. First step is going to be looking for the ionic compound. Second step is going to be split the ionic compound. Third is going to be determine who lost the proton and who gained that proton. And if there are any spectator ions, disregard them. Okay? So let's start with the first one. let me get my pen here and let me write what you have there. So what did they give you? Let's see. Let me pick up the color. Okay, so sulfuric acid. I'm not going to put a quotes just because it takes space and I don't have a lot of space here. And my calcium carbonate, also in aqueous solutions, will break down like this. So here you have the products of this aqueous solution. Okay, so what's going on here? Okay, I said the first thing you need to do is find the ionic compound. The ionic compound is going to be the one that has the metal. So here you have it, calcium. Okay. The second step is to split it. So let's split it. What do we have here? Calcium. And calcium, if you go to your periodic table, if you don't remember that, is in column 2A. Okay. That means that when it gives electrons away, it will develop a positive charge of 2. So what is left here? The polyatomic ion, carbonate. Okay, there you go. So you have split it now into 2. What happened here? Okay, what happened here? This is a covalent. Okay, it's a covalent compound, and if you notice, it looks almost like this one right here, except that instead of having the 2 right here, now it has a 1, and it has now a charge because it lost something. Well, what did it lose? It lost one of the hydrogens. Hope everybody saw that. So basically, one hydrogen went goodbye from here. Who gives protons away? The acid. A minute ago, I should not have said the name of this compound, but I gave it away. I said that it was sulfuric acid. But if I had not said the name, you should have reasoned that those 2 were the same, except that was missing one of the protons, one of the hydrogens becoming negatively charged. So this is your acid, not only because I told you the name, but because you can see that it's missing one of the hydrogens. So what happened here? Let's analyze it. We get a different color. This right here is the same as this right here. It appears in the reactant and the product side. We know that this is a spectator ion. What happened to this ion right here? Well, you see this section is right here, but now is attached to a hydrogen. So basically this hydrogen right here from the acid attached itself to this polyatomic ion. So this is your base. Okay, and that's all you needed to do here, except that this base was part of this. This is your base and this was your acid, and that's all the problem was asking you to do, is identify who is the acid and who is the base, who's giving them away and who's receiving them. Okay, so we have 1 done, several to go. Let me get white. The next one looks like this. It also in aqueous solution, so in water and sodium. I should not be saying names because that could give it away. I'm not going to give away the names right now. Okay. So first step is identify the ionic compound. Well, the ionic compound is right here because we have our sodium. Second step is break it down. Okay, break down that ionic compound. So sodium, column 1, hydroxide is one of your polyatomics, negatively charged like that. Now, compare to see what's going on here. What's going on? Okay. Well, here's another ionic compound. we should probably break it down too, so we can study it a tiny bit more. Okay, so break all your ionic compounds. What else do you notice here? I notice this water seems to be coming out of nowhere. But water has 2 hydrogens and 1 oxygen. Correct? So this had to come from something attaching itself to something else. Well, how about if this hydrogen right here attaches itself to this hydroxide ion right here? What do? Well, they create water. Okay. This is spectator ion because it appears here and it appears there. And this chloride ion came from the hydrochloric acid losing this proton right here. So now we know who is the acid and who is the base. This one gave the proton to the hydroxide section of this sodium hydroxide. This was your acid and this was your base. There you go. That's all you need to do for this section. And that's what you need to do. Be methodical. Break all the ionic compounds. Look at them. Okay. Find the ionic compounds, split them. See who lost a proton, who received that proton. If they're ionic, spectator ions, disregard them. And then you'll find out who is the acid and who is the base. So let's erase these. And let's do one more example from the book, and then we're going to do several more from extra practice problems. So it looks like these. Also in water, so it's all being dissolved. I'm not giving you any names right now, so I don't want to give anything away. And that was the liquid one. I'm going to just put the one that's different. It's liquid. It's water liquid. Okay, so the first step we said was identify anything that's ionic. So it has to have a metal. So here's one and here's the other. Break them apart. So magnesium is in the periodic table in column 2A. It's going to have 2 positive. And it says that this section of this hydroxide, there are 2 of them. So if there are 2 of them, it means that you have this. Okay, that's what you have. Okay. Same thing here, magnesium 2 positive, and you have an O3 negative and O3 negative, and you have 2 of them. Well, as you can see, the magnesium appears here as an ion and appears over here also as an ion, so that's a spectator ion is out of the equation. Now, do you see anything appearing that was not here? Well, you have water right here, and we know that water can be a base or it can be an acid if it was on the reactant side, but it's not there, it's on this side right here. But it looks like it was created by what? Well, this right here, if it attaches to a hydrogen, will create water. So who gave those hydrogens away? Well, we have 2 molecules of water, we have 2 hydroxides. Each one can create a water if they receive 1 more proton. Well, it looks to me like there are 2 of them right here, correct? So that's what happened. This molecule created 2 protons sorry, I don't know why I did that. It should be just 1 negative. Okay. And but there were 2 of them because there were 2 molecules of these. And they traveled, those 2 hydrogens attached themselves to those 2 hydroxides and created the 2 waters right here. Now we can determine who is who. This molecule right here is the one who produced the protons. So this is your acid. I'll put it in blue. This is your acid. This one right here, this section is the one who took them, but the whole molecule is your base. And you are done analyzing the equations. Let's try to do some. You can try on your own first if you want to, and then see how they are done if you are not getting them. But I'm going to work on them next. This is a video, that means you can speed it up, go back, look at it again as many times as you need to understand this section. If you still don't understand, ask me questions in the week or when we meet for our Zoom. So let me clear these and let's look at the extra practice problems. The hydronium ion. Okay, so if this one picked it up, it's going to be the base, but who gave this proton away? Well, it looks like here one of the protons left here, becoming probably like this. Okay, and then it attaches up to the water to give this hydronium ion. So now we have identified who gave it away. This is going to be our acid, and this is going to be our base. So we didn't identify the two players in this reaction. And that's all you needed to do at this stage in the module. So number 2, the second reaction looks like this. Okay, let's look at each one of them. Remember, step number 1, identify any ionic compound. Do we have any? Well, yeah, we do. Here we have potassium. So break it down here kind of as well. Okay? But maybe we'll not need to do that. Okay, break it down. Second step, by comparing the two of them. Okay. This is not a very nice C. It looks like it's a C, and this is a 2. Okay. By comparing the two of them, I can see this is a 5. Sorry guys, but the mouse sometimes, I see that I have created a water, and I know I can create water if this hydroxide ion receives a proton from someplace. Well, who could have given a proton? It looks like this molecule and this molecule are almost the same, except that here I have a 6 and here I have a 5. Okay, so this one lost a proton in this reaction. So this C2H5O negative lost the proton, and that proton, it's another color, got together here with that hydroxyl ion to create the water, and then the remaining ions bonded with one another to create this compound right here. So now I know who is who, don't I? This one right here received the protons. This is my base, and this right here gave them away. So this is my acid. So a lot of times an acid will have the hydrogens in the beginning of the molecule. That's one way to identify an acid. They will have hydrogens as the first element in their formula. But not always. Sometimes they're in the middle, like in here. And then you need to check to see if there's been a change in the number. If you lost the proton, you can bet that this one right here gave them away. Okay, so this one is done. Let's do the last one of the extra practice problems, and you're gonna get to do some more this week with your on your own. So number 3 looks like this: 2HCl, magnesium, and then 2 the water plus MCl2. Okay. Maybe I should let me make it smaller so it fits. Okay. So first step is identify ionic compounds. Here's one, which here you're going to have it too. But we're trying to find acids and bases on the reactant side. So let's concentrate here. So we have magnesium, periodic table, column 2A. We know that it will develop two charges that are positive, and there are two polyatomic ions of the hydroxyl ion. Okay, it needs to compensate the two charges right here. Okay, what do I see here? I see water that was created by those two combining with protons, hydrogen ions. Well, there are two right here. Into chlorine ions, because there are two molecules. There are two molecules of this kind right here. Okay, so what happened here is that those two right here combined with those two right here to make the two waters that you have right here. So this molecule, which is hydrochloric acid, in case you don't remember from me saying it a minute ago, this is your acid, and this one right here is your base. It accepted those protons, so gave it away, acid, took them, your base, and you're done with this kind of problem. This is as much as they're asking you to do for this section of the module. And remember, if you have questions, ask. Okay. Recognizing acids and bases from their chemical formulas, page 327. With a few exceptions, most acids have at least one hydrogen as the first atom in their chemical formulas, but not always. Usually, but not always. With a few exceptions, most bases have the hydroxyl ion in them, but not always. Here are some exceptions. We just saw this acid right here. This is acetic acid. So C2H4O2 is acetic acid. And here's another exception for the bases. So in this case, they don't have the hydroxyl ion, which is ammonia. This right here is not a base. You're going to see this compound in a reaction soon. And don't be confused, this is not a base, because the OH in this is not a hydroxide ion. This compound right here is not ionic. So that's why sometimes the formulas are tricky, and it's better to follow those protons. Who's giving them away? Acid. Who's receiving them? Base. So you have a general statement here, most acids, most bases, but there's exceptions to the rules. So you may want to memorize those exceptions to the rules because you're going to see them in problems. Now, table 10.1 on page 328 are some common acids. Okay. You do not need to memorize this table, but you're going to see them. Hydrochloric acid, sulfuric acid, nitric acid, ethanoic or acetic acid, methanoic or formic acid, and citric acid. So this one had the hydrogen, this had two hydrogens, this had a hydrogen to give, this one was one of the exceptions that did not start with a hydrogen. It has hydrogens to give, but it's not at the beginning. This one it does, and this one it has it in the middle. Okay? How acid an acid is different for different acids. Some are strong acids and some are weak acids, and you're going to see that in more detail pretty soon. Okay? So hydrochloric acid is a strong acid, and you find it in the stomach, also in the lab. Sulfuric acid is a strong acid. It's found in acid rain, in car batteries, and also you can find it in a lab. They sell it. Then you have nitric acid. It's also strong acid, acid rain, and also commercially you can buy it. You can buy it in a lab. Ethanoic or acetic acid is a weak acid and is found in vinegar. And you're going to be working with vinegar quite a bit this year, okay, in your labs. And then we have formic or methanoic acid is a weak acid. Ants, when they bite you, it's itchy because they have formic acid in their bite. You can also find it in nettles, in the stings. So things that itch, sometimes they have this formic acid. And the citric acid also is a weak acid, and you find it in the citrus fruits like lemons and oranges and so on. Okay? So you don't have to memorize these, but this is just an example of acids. Some acids are strong, some are weak, and the same for bases. Some bases are strong, some are weak. Let's talk about polyprotic acids. That's on page 329. Poly means more than one. Protic means they're going to give more than one proton. So they are acids that are able to give more than one proton. A monoprotic acid, mono means one, has one ionizable hydrogen. So I mean they only have one hydrogen atom that can become a hydrogen ion or proton. Okay, hydrogen ion and proton are the same. So that's a monoprotic acid. Only has one that's able to ionize. A polyprotic acid, on the other hand, has more than one that is able to ionize per molecule. So if you look at them, they have 2, 2, 3. So the hydrogen that they have to give away is in multiples. 2, 2, or 3. When they have 2, it's called a diprotic acid because it has 2 to give away. Triprotic acid means it has 3 to give away. What do you need to know? The definition of a polyprotic acid. You also need to know what mono, di, and triprotic means. So mono 1 to give away, di 2 to give away, 3 to give away. The protons of a polyprotic acid dissolve in steps. So sometimes they only give one. They may have 2 to give away, but they only give 1. It just depends on who they are paired with. If whomever is next to them is very strong, it will pull the 2 of them away, for example, or the 3 away. But if they are paired with a very weak base, maybe the base is only strong enough to pull 1 of the protons away. Okay? So there are steps. They're not all taken away at the same time. Definition: polyprotic acid, an acid that can donate more than 1 proton or hydrogen ion. Now, page 328, naming bases. If the base is an ionic compound, so it has a metal, follow the rules of naming ionic compounds. How did we name those? We named the first one, the metal, strontium, and then we added "ide" at the end of whatever you have there, hydroxide. If the base is a covalent compound, chemists call them by their nicknames. So I'm sorry to tell you there is no naming them. There's not a rule to name them. You just have to learn their names. For example, you see this NH3, which should be named nitrogen trihydride. Okay, that's not how we name them, because for the longest time there was not rules to name things. Things were just named. This is ammonia, and you're going to need to know that this is called ammonia. Now, predicting reactions between acids and bases. You already know that acids give away protons, bases take them, so this is a match made in heaven. One likes to give them away, one likes to take them. When you have a base, so you have a compound that will take those protons that contain the hydroxyl ion, okay? You're going to have a reaction that's called a neutralizing reaction. And the products are going to be like this. You're going to have your acid, your base. You're going to create a salt and a water, because the hydroxyl ion will combine with the proton to create water. And the rest of the ions will make this ionic compound. Salt is not table salt, it just means ionic compound. This is called neutralizing reaction. They're not base or acid anymore, because acids and bases can be corrosive, but you have salt and water. And remember that salt is just another name for ionic compound. It doesn't mean table salt, okay? Although in this case it is table salt. Okay, so hydrochloric, here is the proton that will attach to the hydroxyl ion to create this water. What's left? The chlorine and the sodium. So those two ions will combine to make the salt. More examples. Potassium hydroxide. So here you have your potassium and your hydroxide. They broke them down into the ions. Combining with hydrochloric acid, here you go. The hydrogen of the acid will combine with the hydroxyl ion. Those two create what? Create water. Always water. This is a neutralizing reaction because we have a base that has OH negative as a hydroxyl ion, and that's always the procedure. If the base has hydroxyl ion, create water and a salt. Okay, and the two other will get together because they have opposite charges and they're attracted to one another. So there you go. Potassium chloride. Let's look at more examples. Page 331, example 10.2. They say, there are three sections. Give the balanced chemical equation that represents the reaction between the hydrochloric acid and the rubidium hydroxide. Write the chemical equation that describes the reaction between sulfuric acid, they give you the formula, and the sodium hydroxide. And what is the reaction that occurs between the nitric acid and aluminum hydroxide? So they all contain hydroxide. They're all neutralizing reactions. They're always done the same way. Now we're going to do 2 extra practice problems. Let's get started. Okay, let me go to the blackboard here and let's tackle the first one. Remember that they all are going to be like this. Acid plus a base. You have to create a salt plus water. Okay? So remember to do this. The first one, you have your hydrochloric acid, your base here, rubidium hydroxide, and well, I probably should not give it directly to you, should break it down so you can see. Okay, so here is your hydroxyl ion. It will combine with this proton right here to create your water. So here's your water, H2O. And what is left? You have this right here, which is a negatively charged ion, and you have your rubidium, which is positively charged ion. And you're going to put them together. And remember that the positive always goes first. So you're going to end like this, but you're going to leave it pretty. You're going to leave it like this for me. So when you give me your answer, it needs to look clean like this. And then you say, I'm done. So you can break it into pieces if you want to. That helps you see how it's worked. Or you just directly write the equation. Whatever works for you, I'm happy with either one as long as you keep the same number of atoms coming in and coming out. Remember, stoichiometry. Oh wait, I should have erased this too. I'm going to leave the top because they all need to be neutralized. So the second section, they want you to combine sulfuric acid and sodium hydroxide. And remember what we said, okay? Anytime that you have a base with OH, you're going to create water. Well, for this to create water, it needs to combine with one of these hydrogens right here. Let's do that. H2O is being created. You only use one of these, so this is like this. Okay? But you also have a sodium that is floating around. Those two are attracted to one another, so they will get together to create that salt. And remember to put your metal first. So sodium and oops, I almost made a mistake. Remember that there are two here. There are two here because this has to be two negative to if you need two hydrogens to combine with this polyatomic ion, that means that the charge of this polyatomic ion is 2 negative. Okay? So be careful. This is a common mistake. Just be careful. So you have 2 of these. Okay, so if you have 2 of these, what is going on? To create water, you're gonna need 2 of these to create water. Oh, goodness gracious. Okay, it's been a long day. Okay, negative. Okay. You're gonna need 2 hydroxyl ions to create water. These will create 1 molecule of water, and these will create another molecule of water. So you're going to create 2 molecules of water. And what are you going to be left with? 1 and 2 sodiums, which is perfect because you have 2 negative charges to neutralize. So you're going to have 2 sodiums and this polyatomic ion to create a salt. Now, are we gonna leave it like that? No, you should make it all pretty like, okay? You should give me something like this. Sulfuric acid plus sodium hydroxide will give me the sodium sulfate plus the 2 waters right here. And this is what you need to give me. You need to give me the final product all pretty like. Okay, and be careful, okay? Just remember how many charges each one of those polyatomic ions have. And this is a clue. If they are combined with 2 hydrogens, it's because you needed to neutralize those 2 negative charges right here. Okay, one more example and then we're gonna go and do some extra practice problems. So here you go. The last one. Nitric acid and aluminum hydroxide. Gives what? Okay, let's break this correctly. Okay, this time, let me pay attention. You have 3 of these. So you have 1, 2, and 3. And if you also go to the periodic table, you'll see that aluminum is in 3A, column 3A, because it has 3 positive charges. Okay, so you need a 3 to make this aluminum happy. Now, in this case, to make water, you're going to need 3 of these molecules because you need 3 hydrogens to make water right here. So I'm going to need 3 of these to provide me with the 3 protons that I need to make water. But you also are creating 3 of these polyatomic ions. Now, the hydrogens and the hydroxyls are going to be getting together to create 3 waters. Each pairs to create 3 waters. So that's done. So what is left here? Well, you have the aluminum that needs 3 negative charges to make him happy. Well, the aluminum is going to be happy with that molecule. Now, remember that if you have more than 1 polyatomic ion, you need to open parentheses and put it inside the parentheses how many of them you needed. So you needed 3 of these polyatomic ions to combine with the aluminum to create that salt. So acid, base, salt, water. And then make it all pretty. Okay, here we go. So the way to write this down is I need 3 of my acids to combine with my base to make my salt and my 3 waters. And that's your answer. That's your final answer. That's what it needs to look like. So let's practice a tiny bit more. The more you practice, the better you get at this. Let's clear this and start with extra practice problem number 4. Let me find my notes. Okay, let me read it. Now I have my notes in front of me. I can read it. So number 4. And those are on page 578, okay? So number 4 says, what is the reaction between, and they give you 2 compounds. So those 2 are going to be combining to create something. Well, as you can see, you have the same base as you had before, the aluminum hydroxide here, okay? So you know that this is your base. It's a base that has hydroxide. That means you're going to be creating a salt and a water. Salt plus water. So let's do that. The first thing is break everything apart. You have 3 of these, 1 aluminum, positive 3, and then you have this right here. That's where the hydrogens are coming from this acid right here. To make each hydroxyl happy, you're going to need 3 of these. You need these times 3. Well, what do you have then? 3 protons, and you also are left with 3 iodine ions. Okay? So now we can combine my 3 protons with my 3 hydroxyls to make water. How many am I creating? I'm creating 3 waters. Well, now the water is created. Now I have to create the salt. The salt has the metal first. So I'm going to put aluminum. How many of these? 3. It's not a polyatomic, so I just put the 3 right here. Okay? So clean it up. And you have your answer. So it should look like this. And then you're done. Okay? This is your answer right here. You know, I like things boxed, because when you have a whole page of stoichiometry, sometimes you get lost in the middle, and I want you to box your answer to make it easy for me to see where it is. Okay, so this is done. Let's do number 5. I think that was the next one. Yeah, number 5 is the next one I wanted you to do. So for number 5, it says, what is the reaction between, and they give you an acid and sodium hydroxide as a base, and it's another base that has the OH right here, so it has the hydroxyl ion. That means you're going to create salt and water again. It's a neutralizing reaction. So break it apart. What do you have? You have a sodium and you have the hydroxyl ion. Well, you only have the one that you need to make happy. If you only have the one, you don't have to break the whole thing. You only, not only that, but let's continue analyzing this. Well, I know that this is a polyatomic ion. I know that for this polyatomic ion to be happy, I need 3 hydrogens, so 3 charges right here. So if I didn't remember what the charge of this was, I can look it up. Or I can say I need 3 to neutralize, so that means probably that this is like this. Okay? So what does that mean? That means that I have 3 protons. I have a polyatomic ion that needs 3 negative charges to neutralize, but I only have the 1 sodium right here to neutralize it with. That's not going to work. So I need 3 of these. I need this times 3. I get this by having 3 of these molecules. Everybody sees that? So if I have 3 molecules of these, I will have 3 of this sodium ion, and 3 of them can get together with this polyatomic ion and neutralize it. But if I do that, I also get 3 of these. Okay, if I have 3 of these, I can create 3 waters with the 1, 2, 3 protons that I have. I will do that. Okay, let's do it. Okay, and then where is my salt? Well, I mentioned to you a minute ago that this one right here needed 3 sodiums to neutralize the charges. So you need to mention the positive first, your metal, and that is Na. How many of them? 3. And how many of these? It was only the 1 polyatomic ion, so we don't have to put it in parentheses. And then you are done, and you make it look pretty. So write it like this. Remember that I'm using parentheses and stuff like that just to emphasize my thinking process, okay? We don't put parentheses in front of our stoichiometric coefficients right here, our moles. And this is what you need to box. This is your answer. And then you are done for this one as well. You neutralized it. You neutralize the acid and the base by creating a salt and water. Let's erase these. Let's go back to instruction. Did I? Just a minute. Yeah, we just did this right here. So here, we're almost done. Predicting reactions between acids and bases. With covalent bases. So we saw ionic bases. So, with the hydroxyl, it broke apart the ions, and then you start looking at the other ions and see who's going to be mixing with whom. We're going to create water, we're going to create a salt. But now we have covalent bases. So how do we predict those reactions? For example, sulfuric acid and water. Remember that this is amphiperiodic and it can act as a base or as an acid. So if this was an acid, now the water is acting as a base. Okay. We know the acid will give the protons and the base will need to receive the protons. That's a definition of an acid and a base. So here you go. You have your sulfuric acid, you have your water. You know that this one needs to give it away, those protons, and this one needs to receive it. Okay? If water receives 1 extra proton, this becomes a 3, and it becomes positively charged. And what happened to the sulfuric acid? One of those protons left. So now it's only left with 1 proton and a negative charge. Well, this is the product. It can give 2 away. It could. So let's look at this. If it gives the 2 away, what are you left with? You're left with this polyatomic ion, and now you have created 2 hydronium ions. So 1, second step, create a second hydronium ion. Steps are important, okay? So sometimes it doesn't go to the second step, sometimes it stops after the first step. In this case, for this example, they went all the way and it gave 2 protons away. Okay, apply these to this example, and then we're going to do some practice problems, extra practice problems 6 and 4, to cement this information. Example 10.3 reads like this. It's on page 333. And this is the last one. So, what reaction occurs between phosphoric acid and ammonia, which is the base? Well, we know the ammonia is the base, is a covalent base. And then you have another acid, chromic acid, and water. So water here again is the base. We have those 2 examples. Let's go to the board and see how we break this down. let me write down the first part of the equation. So they give me the phosphoric acid, and I'm copying the formula, and they're giving me ammonia and H3. That's all I know. I don't have anything else in here, but I know that my acid gives away protons. Where are they? They are here. How many? 3. If this needed 3 protons, that means that this has a charge of -3, in case you didn't remember. This is my base. I'll write it down. Acid. And this is my base. By definition, the base will be taking those protons. Well, each one of them can take 1 proton. That's the way it works. So I'm going to need 3 of these to take each one of them. So what am I creating? I'm creating 3 NH4 positive, because it has become positively charged. What is left? This polyatomic ion. Put it here at the end, and you are done. That's a phosphate ion. Okay, that's a phosphate ion, and that is your answer. Just follow what we learned about acids and bases when you have a covalent base. Acid gives protons, base takes them, and then create the molecules that come out of doing that. So let's do the second part of the example. They give you chromic acid, so I don't like to use blue at the beginning. H2Cr2O, and it will combine with your water. So here you have your acid, and this is going to be your base. So your acid gives them away, base will take them. Here to give away, here you're going to be adding them one at a time. Okay, each one can take 1. So here you go. How many? You have 2 to give. That means that this is a polyatomic ion with 2 negative charges. Each water can take 1. I have 2. So I'm going to need 2 waters to be able to take those protons. And then what are you going to be left with? Well, you're going to be creating 2 hydronium ions, which are a water that took one of the protons and it becomes positively charged. And then the polyatomic ion that's left over, the dichromate ion, Cr2O7 2 negative. And that's the answer. That is all you needed to do. So in a way, they're kind of easier than the ionic bases, creating a salt and a water. At least to me, they look a little bit easier. Okay, let me get my extra practice problems, and let's do the 2 that would be nice for you to do. Let's look at the problem right here. Number 6. It's tricky. Number 6 is tricky. So be careful with this one. So here you go. They give you this as, what is the reaction between, and they give you a molecule. They don't tell you who is who. And maybe you remember who is who. We know this is the acid, okay? Phosphoric acid. So we know that this will break apart into the proton ions and this polyatomic ion with 3 negative charges. So if this is the acid, this has to be the base. Okay. I see hydrogens here. That's where they're going to be going. Those protons need to go in this section right here of the base. That's where I'm going to put them. And we have seen a base that had hydrogens here in the middle. How many hydrogens do I need to assimilate into the base? 3. So I'm going to need 3 of these kind of bases to take each one of them. When I do that, I'm going to create 3 molecules that look like these. Here is the proton that is being assimilated, and because it's a proton coming in, they are charged positively. What is left? This is left. The phosphoric. Oops, that's supposed to be 4. 3 positive polyatomic ion. And that is my answer. There's nothing to add anymore. There's no salt and no water because this was not a hydroxyl a base with a hydroxyl polyatomic ion. Okay? Okay, let's erase. Me during the week if you need to with questions. Review all the examples if you need to. Work through them on your own. And correct them as you go so you don't make the same mistake over and over. Study for your quiz. Do your lab. There's a lab. Ask questions if you need to. And study to take your test. And that's it. Have a good week.